Hello and thank you for watching. In this demo, I will teach as I would in my IB classroom through questions, interaction and discovery. Good morning everyone. I hope you are all doing great today and you are ready to learn some physics with me. Because today we are going to explore one of the most beautiful motions in physics, simple harmonic motion. And trust me, it's literally everywhere. In your earphones, in car suspensions, inside every atom where particles oscillate in energy levels. So if we understand simple harmonic motion, we understand a huge part of physical world and how the world moves. Look at this motion, just back and forth, right? So group A, could you please tell me if we track this position over time, what shape do you think we get? Exactly, that's a wave. You are already thinking like a physicist. So let's imagine a point around a circle at a constant speed. So let me draw a circle. Imagine this one a round table. So we can move it. And imagine here I put a dot or I mark the place and I turn the table counterclockwise. So the motion will be like this. But if I look from the side, I will see the object or I will see the dot as projectile on an x-axis. It will be like this. What shape is this? Is it cosine or sine? Yes, it's exactly a sine wave. So this will create a sine wave. And then that's why we use radians, because the motion comes from the circle. So if the circular motion creates a sine-like movement in time, can we write that motion mathematically? Yes, we can. So the dot were here at the beginning. So I'm going to put a triangle here. So this is the projectile of the object. This is the x-axis. And imagine that here is x, this part. So this is the radius already. How we can write the trigonometric equation here? Cosine theta equals adjacent over hypotenuse. So here, adjacent is the x itself over the radius. So from here, I can write the displacement equation cosine theta times r, or r times cosine theta. So let me drive this very quickly. Phase angle simply tells us where we are in the cycle. Are we at the top, at the bottom, or just passing the center? It's an easy way to describe the motion at any moment. And here we go. Position is just the projection of circular motion. Nothing more mysterious. And this angle, omega t plus phi, tells us where we are in time. And x0, the maximum displacement here, tells us how far we can go, the amplitude. The single idea connects geometry, physics and time beautifully. And it's also shown that we can describe a complex motion with just one function. That's the elegance of physics. But there is something missing. We can see where the object is, but what makes it come back? So let's figure out the force behind this motion. Let's have a quick check. When the object is here at the edge, where does the force point? Would it be? Exactly, always to the equilibrium. That's why we get a minus sign in simple harmonic motion. The force and acceleration are always restoring. So imagine this one. If there is no air, if there is no damping, this will oscillate forever. Imagine that there is no air, there is no damping, there is no friction. nothing else. It will oscillate forever until there will be another force acting on it. So now that we know what forces bring it back, so let's look at how fast that motion happens. How we can find the velocity of this object? Velocity is the derivative of the position. If we take the derivative of the position, so this will be the velocity, which we can find how fast that motion happens. And it tells us how fast the position changes, and the mass confirms what we already feel. Fastest at the center, zero at the extremes. Here we have the pendulum, so it will be fastest here at the center. And then again, it will stop at the edge and then come back. And this is how we can find the velocity for simple harmonic motion. So watch this spring, slow here, fastest in the middle. As the spring stretches, it stores energy, and energy is constantly slipping forms. And notice, it doesn't go on forever. That's damping. You see? Let me define what's damping here. Damping implies any mechanisms that steals energy from the system, like air resistance or friction. This means that if there is no air resistance and no friction, a system in simple harmonic motion would never stop. It would oscillate forever. So this is pure physics in motion. By using the sine square plus cosine square is equal to 1, we eliminate the phase angle and express velocity purely in terms of displacement. And the plus and minus sign tells us direction of the motion. So let's look at the energy in simple harmonic motion. We have total energy, which is the sum of potential and kinetic energy. By using K equals m omega square, the total energy is simple harmonic motion depends only on amplitude, because that's where all the energy is stored. At any point x, some of that becomes potential, the rest becomes kinetic. And this will be the total energy, which equals to the kinetic energy of the object plus the potential energy of the object. So how we can define the total energy? Imagine that the object is at the maximum displacement. So 1/2 k x 0 square. So instead of k, I'm going to write here m omega square x 0 square, which is the maximum amplitude square. And this will be the equation for total energy in simple harmonic motion. So the potential energy is 1/2 k m omega square times x square. So this equation tells me that at random displacement, the potential energy can be described as this. So energy keeps the oscillation alive. Simple harmonic motion plus the propagation creates the waves. Simple harmonic motion plus the propagation turns into waves. Simple harmonic motion isn't isn't just a concept, it's the engine inside every wave model. And the most powerful example here is how we generate electricity. We don't generate sine waves, we generate rotations. So the sine waves are just the shadow of that motion. AC power grids are built on simple harmonic motion, and this is literally how our home gets power. So here I want to mention some examples. The first one is Faraday generator, a rotating magnetic field projected onto the coil axis, so it turns sinusoidal EMF. Our AC power is just the shadow of that rotation. And secondly, we have analog radio antenna. The rotating electromagnetic field vectors projection on antenna axis, sine voltage. And the radians don't make sine waves, they receive projections. And the third one will be the microphone, sound to electricity. Air molecules vibrate and diaphragm oscillates. Again, sinusoidal signal. The sound we hear is the shadow of those vibrations. And the fourth example will be car alternator charging system. When we charge our phones in a car, we use the rotating shadow. The engine belt rotates, the magnetic field rotates, so it turns out the AC and rectified to the direct current, DC. Even molecules in the air vibrate like tiny simple harmonic systems. Greenhouse gases absorb infrared energy when they oscillate, and the more oscillation means more trapped heat, and that's the enhanced greenhouse effect. From the climate around us to the power that lights our cities, simple harmonic motion is everywhere. From the power that lights our cities to the music that moves our hearts to the sensors that count every step we take, look closely, and physics is everywhere. It doesn't begin in textbooks, it begins the moment when you learn how to see.